Yeah, so a very warm welcome to everyone. Thanks for having us here. Thanks for giving us the opportunity and platform to put forth our progress and our pod. So we are Team Vegapod Hyperloop, myself Shubham, and my colleague Saksham. We will be taking you through and showing you what we have done in the past years and presenting our full pod. So I'll take a brief moment to talk about our team. Our team began in the year 2018. So this is the fifth year of our team. Uh, we have been 3 years into, we have made three iterations of our pod up till now. The third one being the relatively advanced one. Uh, we are a team of 34 undergrad members from different backgrounds of engineering. So without any further ado, let's just get into it. This is the first look of our last year's pod, which we made. Almost all the subsystems that we made have been mounted here except the aeroshell. So uh, you can see all the systems mounted here. Talking about the goals which we had in mind before making this pod, they were just to get closer to the concept of Hyperloop as such. Mm, for one of them was to inch closer to the concept of contactlessness of the Hyperloop pod. We also aim to make the pod more sustainable and a lot cost effective. So getting right to the uh, into the topic, we start with the structures. We decided to make a aluminium monocoque for the chassis. We decided to go towards the route of a staggered aluminium chassis, so as to give more strength to the parts where it was needed. Like you can see, the chassis was 8.7 kgs, capable of lifting around 10 times of its own weight, so very efficient. And just to put a image of scale in your head, it was 1.2 meters long. It costed us about 35,000 rupees, so everything was done in-house. The manufacturing process of the chassis was pretty straightforward. We first designed the chassis in-house, optimized it, then uh, laser cut the chassis, and then bent it into the desired shape we wanted. Moving to guidance, we had two setups, the lateral setup and the front setup. The front setup was relatively straightforward. It used a coilover damper bell crank mechanism. So the main aim of this setup was to negate any track irregularities and maintain a constant air gap for the linear induction motor. The lateral setup is where we went contactless. It was not completely new technology as such, but it was a pretty innovative application of a previously existing tech. So we made a circular hallback array consisting of 12 neodymium magnets. We connected them to motors, and we spun them to about 5,500 RPM. Uh, and the opposite forces generated in the aluminum track gave us a stabilizing and repulsive force, so that the track does not derail and maintains its straight motion. Here you can see a testing video of our CLS. Again, everything in this system as well was made in-house, or yeah. Furthermore, the CLS utilized a closed loop feedback system using a PID. So our the RPM of the motor was always autonomously regulated with respect to the distance from the chassis. Coming to the braking system, we had two braking systems, a pneumatic redundant braking system and eddy current braking system. Talking about the pneumatic system, it by far the most important system when it comes to safety of the pod. So our braking system was capable of delivering a force of 1100 newtons, which produced 1.25 Gs of deceleration. We used a pretty unique design for the actuation. We used a wedge mechanism, which gave us a mechanical advantage of around 3. So our braking force was multiplied by 3. More about eddy current will be explained by Saksham.
Hi, I will be continuing the presentation. So one of our goals was to achieve as many non-contact subsystems as possible. So we designed an eddy current braking system. So this consisted of 4 linear hallback arrays, and each of these hallback arrays consisted of 9 N52 magnets. So N52 magnets were utilized in order to maximize the performance and braking force of the system. So also for attaching the linear hallback arrays to the pod, lead screw mechanism was used to bring the hallback arrays close to the track. This maintained a air gap of 5 millimeters, and our setup produces a drag force of 580 newtons at a speed of 75 kilometers an hour. Next slide. So this is the setup of the fail-safe eddy current braking system. This is mounted on the underside of the vehicle, and it actuates both the sides of the linear hallback arrays across the I-beam. Next slide. Inching closer to the non-contact prospect of the goals, our propulsion system used a single-sided linear induction motor. A linear induction motor was chosen due to the simplicity and cost effectiveness of the system, and it was powered by a 8 kilowatt AC source. So it required a 3-phase AC current in order to be powered. It had 18 slots of stacked silicon steel core, and it had 80 turns per slot of winding. So its winding was capable of carrying a current up to 40 amps, and it was fully developed in-house. Next slide. All the development and manufacturing of the LIM took place in-house, and the stacking of silicon steel sheets up to the winding of the windings took place in-house, and the final motor looks like the following photos. Next slide. Next slide. So in order to power the linear induction motor, as I just stated, 3-phase AC source was required. So as our power systems were operated off of DC batteries, power electronics such as inverter were needed to convert the DC source into a 3-phase AC source. So in-house 3-phase inverter was developed. This inverter utilized a sinusoidal pulse width modulation technique in order to convert direct current into AC current. So this inverter could be controlled over CAN protocol, which helped with communication with the rest of the electronics. And since the linear induction motor also required V by F control, it had to be a VFD, and hence it had a V by F ramp up sequence. It was capable of a current of up to 150 amps RMS per phase. So this is a quick peek of the inverter which we developed. This was taken during the testing phase of the inverter. Next slide. Next slide. So for our power systems, we actually went ahead with 3 different power systems, namely high voltage, medium voltage, and low voltage power systems. And each of them had a different purpose. So high voltage battery pack was used to power up the LIM, used to power up the inverter, which in turn powered up the LIM. Its voltage was 177 volts nominal and had a capacity of 12 amp hours. It consisted of like lithium polymer batteries. Switchgear was in place to protect the high voltage system, and the switchgear consisted of the insulation monitoring device, manual service disconnect, contactors, and also emergency stop and fuses, which directly cut off the power from the battery pack to the system in order to protect the system. Medium voltage battery pack was also present. That was used to power the contactless levitation system, which we achieved this year. And this was basically used to spin the BLDC motors, which were used in the contactless system. It was a 37 volt 10S lithium polymer battery pack, and it was also protected by a BMS. Low voltage battery pack was used only to power the electronic systems, which helped in navigation and communication of the pod. It was only a 22.2 volt system, which consists of 6-cell lithium polymer battery. So the total cost of the power systems was only $1,800. Next slide. Coming on to the electronics, electronics were used to maintain the communication and navigation of the vehicle, obviously, and delocalized star topology of electronics system was used, and this consisted of a master central vehicular control unit, or VCU, which was connected to multiple VCUs spread over the pod, which communicated using CAN protocol. So separate control modules or VCUs were used for each subsystem, which further aided in scalability of the pod. STM32s were used as the ARM processors of the system, and M4 based CPUs were used in the MVCU, and M3 based CPUs were used in the VCUs. All of the firmware and code was written in-house by engineers, which included error handling and safety mechanisms, and also fail-safe mechanisms. This also contained data logging from the different temperature sensors and all of the different sensors, such as speed sensors and as such. Next slide. Coming on to the final component of the vehicle is the aeroshell. This is obviously needed to complete the Hyperloop prototype. So we designed a aeroshell in-house also. We developed the aeroshell using a different material than the rest of the teams. So we developed it using flax fiber, and it was manufactured in-house using resin infusion, just like carbon fiber. It had a maximum achievable speed of 350 kilometers an hour, and it had a drag coefficient of 1.19. And it only weighed 12 kg, with while boasting a factor of safety of 7.79, which further demonstrates the use of flax fiber. These are some of the photos which were taken during the manufacturing process of the aeroshell. A mold was created, and then flax fiber was laid down in the mold, and then resin was infused in order to solidify the aeroshell. Now Shubham will be taking over.
Right. So, like I mentioned earlier, we had 3 major goals this year. One was to get closer to the contactless prospect. Second one was to make the system as cost effective as possible, and third was to make a pretty much sustainable design. The first 2 things I think we have covered in the presentation so far. We managed to do a pretty cost effective. We managed to make a pretty cost effective pod, get closer to contactless nature of the vehicle. The last thing which I want to get your attention on is the sustainability of the mechanical design. Like Saksham mentioned, we used flax fiber instead of carbon fiber. This was done because flax fiber is biodegradable, and in terms of production, it is very energy efficient. We ran out many tests. We conducted many we did lots of tests on samples before actually making the aeroshell and implementing the material. Also very innovative approach was used to make the brake pads. We made the brake pads of the braking system on our own. We used hemp composite, which is again a natural fiber, and cashew resin. We did this after conducting thorough analysis, thorough experiments, referring to research papers and diving into areas where there was no research and conducting our own research. So we made a lot of experiments. We carried out a lot of experiments and we came up with a sweet spot, and we made a brake pad that was 100% sustainable. So this is what set us apart from the rest of the teams globally. Lastly, our sponsors, we would like to thank them. The things we do, it is not possible without their support. So a big thank you to all our sponsors. And yeah, thank you for giving a patient listen to both of us. Vegapod Hyperloop is always open to discussions and growing the Hyperloop community as a whole. So feel free to reach out to us in the below mentioned social media handles. And yeah, thank you for having us.
Thanks, guys. That was great. Nice work. Does anybody have any questions for Vegapod? Feel free to turn on your mic, or you can raise your hand or type in the chat. All right. Well, thank you guys so much for your presentation. That was great. And hopefully we see you at the conference this year.
Yeah, sure, will do.
Great. All right, next up we have Texas Guadalupe. I know we are a little bit, we have a question from Liam for Vegapod. Do you plan to come to the competition this year?
Yeah, so Liam
sure
definitely will be looking forward to participate in your competition. Figuring out the logistics and the current geopolitical scenario is a bit tricky for us as of now, but we would definitely love to participate in your competition this year.
Well, we will try and make it happen.
Yeah, definitely.
Yes, great. Thank you so much. And it looks like one other person has their hand up. Yuming, do you want to turn on your mic and ask your question?
Yeah, I was wondering, how does the team plan to shield the hallback array from the rest of the system?
I'm really sorry, but I was not able to catch your question. So could you please repeat it?
Yeah, I'm wondering, how does the team plan to shield the hallback array from the rest of the system?
So for the linear induction motor and different magnetic parts, we are using electromagnetic shielding. So there is a stainless steel shielding placed on top of the linear induction motor mount, which completely covers up the linear induction motor from the rest of the pod electronics and different subsystems, while only directing the magnetic fields to the track. If that answers your question.